10. Here we have some kind of industrial plant that's operating a large bag house for air pollution control. Now, as you well know, a bag house is a very efficient device, probably the most efficient particulate collection device, certainly over a wide variety of dusts. And there are some limitations, of course, and you simply need to look through the chapters on ESPs, bag houses, wet scrubbers, cyclones, and I think some of those advantages and disadvantages will become obvious. But here we have a bag house. The temperature is 250. The gas is flowing in at 100,000 cubic feet per minute, a large flow rate. The inlet dust loading is 12 grains per standard cubic foot. Now, here's the key. Notice the flow rate is given in actual cubic feet per minute. The dust loading is given in standard cubic feet. Emission regulation for the plant as a whole is in grains per standard cubic foot. This is something that happens quite frequently with regulatory agencies. They don't really care about how you operate your equipment, what temperature it's at, whatever. They're going to write the regulation in terms of standard cubic feet. And they may adjust that even for moisture content or for oxygen content if it's a combustion source. But nevertheless, here we have a situation where the actual flow rate is given, but yet the standards and the concentrations are given in standard cubic feet per minute. How does that affect our calculations? And we do want to calculate the required collection efficiency. All right, so for problem 10, it doesn't affect us at all. The volumetric flow rate given is a distractor. It is intended simply to distract you from the correct approach here. Since the standard is given in grains per standard cubic feet in regulation, and since the actual concentration has been converted to grains per standard cubic foot, you simply subtract them and divide by the inlet to get the efficiency. Notice that the volumetric flow rate played no part in solving that problem. So you have to be on the lookout for that because there will be some of that occurring. Okay, I'm going to take a short break here and we'll come back and begin again on problem 11. Okay, we're back from our break, thank you. And we're looking at, so we just finished problem 10, now we're going to problem 11. And we come across tip number 5. For on the PE exam, the air to cloth ratio for the type of dust and bag house would be supplied. And that's simply to make sure that everybody's using the same factors, if you will, in the problem, because there is some room for judgment on the air to cloth ratio for different kinds of dust and for different dust loadings, and that is explored in the chapter on bag houses. But for the format of the PE exam, where you have multiple choice answers, we need to be consistent, so they would typically give you that number. You wouldn't have to look it up in a reference book. And perhaps different people are using different design values. So we have a fabric filter treating 30,000 cubic feet per minute, actual cubic feet per minute, with an average air to cloth ratio of 2 feet per minute. The bags are 8 inches in diameter, 12 feet long. estimate the total number of bags in the bag house. And again, you're given some good choices here. You're not going to be stuck right in between two choices, hopefully. You'll be close to one of these. All right, so let's look at the solution for number 11. Since the air to cloth ratio is the filtering velocity, V, and that's equal to Q over A, we simply can turn that around to calculate the area. Since we're given Q and V, the area of fabric through which it must be filtering this 30,000 is 15,000 square feet of fabric. Now we calculate the area of one bag, which is the fabric area, pi dl, surface area of a cylinder, without the end cap. Now, some people would include the end cap, some people would not. It doesn't make too much difference, and it's certainly easier to just go through this to calculate 25.1 square feet. If you included some filtering area on the end, you might have a little bit more than that, but it wouldn't change your answer substantially. So the number of bags is simply the total square footage divided by the square feet per bag, equal approximately 600 bags. Okay. Problem 12. A particulate matter size distribution by mass and corresponding collection efficiencies for the same size range for a proposed control device is given in the following table. And so we're saying for particles in this size range, in this particular distribution, we have 10% of the particles by mass are in this size range, 30% by mass are in this size range, 40% in this size range, etc. But also, this table gives you, for the proposed control device, the efficiency in that size range, the efficiency in that size range, and so on. So we have all the information to calculate the overall collection efficiency of the control device. So to this table, we simply add one more column, the percent collected. We have the size range, the mass fraction, the efficiency in that size range, and the percent collected, which is simply the efficiency in percent times the mass fraction in fraction form. And that gives you the number 2. So we're saying 1/10 of 20%, or we're saying 20% of 0.1 is 0.02, which in percentage terms is 2%. So we have 2% collected of the smallest particles, 15% is collected in this size range, 33%. And since the efficiency is 100%, the last 20% of the particles are collected completely. So it gives us a total of 20% of all the particles being collected. And we simply add those together to give us the overall collection efficiency of 70%. All right, now an ESP problem, problem 13.